Section 3, what happens when we have complex solutions? All right, so let's start with, remember, the functions e to the x. Do you remember that it can be written as a polynomial, right, of x to the n over n factorial, where n starts at 0 and goes to infinity. And if we expanded this out, plugging a 0 in, you would get a 1 and then technically an x to the 1 over 1 factorial, and then an x squared over 2 factorial, and an x cubed over 3 factorial. And it goes on forever like that. Also, do you remember cosine of x can also be written as a polynomial? It's -1 to the nth power, and it's all the even powers of x and divided by all the even numbers factorial, where again you start with 0 and go to infinity. And so if you remember this, cosine of x can be written as a polynomial 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And we can do the same thing with sine. Sine, all these little stupid windows, sine of x was also alternated in sign, and it was all the odd powers of on x and divided by all the odd powers factorial. And so this sine of x is approximated by the polynomial x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and all of that. Okay, so we're going to start with those. And let's see what happens when I have e to the ix. All right, so that means I'm plugging an ix into x in this guy. So all of these x's are going to be, you can write it with sigma notation too. So now ix is what's being plugged into x to the power of n over n factorial. We're going from n equals 0 to infinity. Okay, so that becomes a 1 plus an ix over 1 plus an ix quantity squared over 2 factorial plus an ix quantity cubed over 3 factorial plus an ix to the 4th over 4 factorial. Let's do one more. Plus an ix to the 5th over 5 factorial, and obviously it keeps on going. Okay, so what I'm going to do, let's simplify this. So this is still a 1 plus an ix. This guy would end up being I squared, which makes it a -1. Do you remember I to the power of 1 is just I. I squared is -1. I cubed is -I. And I to the 4th is a +1. I won, losers in the middle. Remember that? I and then a 1, I and then a 1, and then the losers or the negatives are in the middle. Just a way to remember. And then remember they repeat after that, right? I to the 5th would be back up here again. Okay, so an I squared is -1, so that makes this a minus x squared over 2 factorial. I cubed is a -I, so you would have a -ix cubed over 3 factorial. I to the 4th is just +1, so that's just an x to the 4th over 4 factorial. I to the 5th, you're back up at I, so that's a +ix to the 5th over 5 factorial. Okay, let's group them. Why am I going to do this? Because I see cosine in here and I see sine in here. Yeah? So I'm going to group them of all of the real parts, so the ones that no longer have i's in them. That would be a 1, and then that has an I in it. I'm going to skip it for right now. Then a minus x squared over 2 factorial has an I in it. Going to skip it for now. Plus x to the 4th over 4 factorial. And of course, it would keep on going. And then a plus, I'm going to factor out the I that's in common to all of these terms that have i's in them, and I would be left with x and then minus x cubed over 3 factorial, and then plus x to the 5th over 5 factorial. Yeah, isn't this lovely? So what does this mean? This means that e to the ix is cosine of x. That's that guy. In fact, I'm going to put parentheses just because we're going to use this later. And then plus I times this guy is sine of x. All right. We are going to be able to get solutions to differential equations using this. All right. So also I want you to remember that if you have e now to the a plus bi, now keep in mind using properties of exponents, this is e to the a times e to the bi, right? Keep the base, they have the same base, keep the base, add the exponent, so that's equivalent. Well, that just means it's e to the a times, now I have e to the bi, which is this guy. Your b is going to be your x, right? So that you've got cosine of b plus I times sine of b. Yeah, which then just means it's e to the a cosine of b plus I times e to the a sine of b. All right, so let's do a couple of real quick little examples. Like e to the 3 plus 4i. Your real part is 3, right? So it would be e cubed times cosine of 4 plus I times sine of 4. All right, because here your a was 3, your b is 4. Okay. Another one. What if it was e to the 3 minus I? All right, well now your a is 3, your b is negative 1. So that means you would have e cubed times the quantity cosine of negative 1 plus I times sine of negative 1. And we can even clean that up more. Do you remember this is an even function, so this is the same as cosine of 1, and this would be sine is an odd function, so it's the same as minus sine of positive 1. We'll do that too. Okay, so we also have the fact now that e to the ix is equal to cosine of x plus I times sine of x, right? We had that from up above. Well, that means that if I've got e to the negative ix, well, that would just be cosine of negative x plus I times sine of negative x. And if you remember that cosine of a negative angle is equal to the positive cosine of the positive angle because it's an even function, and sine of negative x is an odd function, it's equal to negative sine of positive x, which then means that e to the negative ix is also, it's just equal to cosine of positive x minus I times sine of positive x. Now, if we add these guys together, so I'm going to add these two together, it's going to give us another result. If I do e to the ix plus e to the negative ix, cosine of x plus cosine of x gives me 2 cosine of x. I sine of x minus I sine of x, those guys cancel. Yeah? All right, so that means that cosine of x is equal to 1/2 of e to the ix plus e to the negative ix. We also have that we could subtract the two. right? E to the ix minus e to the negative ix. You would have cosine of x minus cosine of x would be 0. And then I sine of x minus a negative I sine of x. It gives me a 2I sine of x, which then means that sine of x is equal to 1 over 2I times e to the ix minus e to the negative ix. Lovely. All right, so what does that mean? Well, if I asked you for what's sine of 5x, we know it's 1 over 2I times e to the 5ix minus e to the negative 5ix. Okay. I really don't want to write this, so I'm going to just show you. So that's where all of those results come from. Let's look at this lemma real quick. If you want to write it, go ahead. I'm not going to. Given W, that's going from taking real numbers to complex. It's defined by W of x is equal to U of x plus IV of x, with real functions U and V going from R to R, with a real linear operator L. Well, if L of W is equal to 0, then L of U is equal to 0, and L of V is equal to 0. Okay. Now, we got a theorem saying that given that real irreducible quadratic operator P of D equals D squared minus 2AD plus A squared plus B squared, you saw that the other day, with complex conjugate roots, A plus BI and A minus BI, where B can't equal 0, because otherwise they're not complex, non-real, right? They would be real answers. The linear differential equation P of dy equals 0 has real independent solutions. Nice. Y1 equals e to the ax cosine of bx, and y2 is equal to e to the ax times sine of bx. So I'm going to go ahead and I'm going to write those down. All right, so we have that theorem. I'm not going to write the whole thing, but given P of D equals D squared minus 2AD plus A squared plus B squared with roots A plus BI and A minus BI, then P of dy equals 0 has they're real and they're independent solutions. Y1 will be e to the ax cosine of bx, and y2 will be e to the ax sine of bx. That's what we're going to use. All right, so let's do some examples. All right, first one. Y double prime plus y equals 0. All right, so let's write this as a polynomial operator of d. This would be d squared plus 1 operating on y, right? Well, this factors as d plus I times d minus I. So your auxiliary equation would just be r plus I times r minus I equals 0, which means r is equal to negative I, or r is equal to I. And so your A is 0, your B is 1. And so that means that, because remember up here, you've got both of them, A plus BI, A minus BI, and then, right, does that make sense? So your A and your B, we're going to plug them into those guys. All right, so that gives me that y1 is e to the ax, so 0x, times cosine of 1 times x, and y2 will be e to the 0x times sine of 1x. Yeah. And these are, our theorem says, these are two linearly independent real solutions. These are two linearly independent real solutions to this equation. So our general homogeneous solution is y equals c1 cosine of x plus c2 sine of x. Because obviously, e to the 0 is just 1, so this is just cosine of x, and this guy is just sine of x. Okay, let's check it, right? Because I told you this before, but just in case you don't know, any solution you get, you should be able to plug into this differential equation and get equals 0. It should satisfy the equation. So let's do that. Yeah. Okay, so let's check it. What do I need? I need y, and I need the second derivative of y. All right, so let's find y is this guy. Y prime would be derivative of cosine is negative sine, so it'd be a negative c1 sine of x. Derivative of sine is cosine, so a plus c2 cosine of x. I don't need that one, but I need the second derivative, so second derivative would be derivative of sine is cosine, so it would be a negative c1 cosine of x. Derivative of cosine is negative sine, so minus c2 sine of x. All right, and what we're trying to verify right now is that my solution, this general homogeneous solution, satisfies my equation, which was, my equation was second derivative of y plus y equals 0. So I plug this guy in. We got a negative c1 cosine of x minus c2 sine of x plus y, and my y was up here, c1 cosine of x plus c2 sine of x. And sure enough, bye-bye, ta-ta, it is equal to 0. So you should be able, some of these answers will be horrible to try to check, but that one is definitely easy that you can walk away going, okay, I know I got my solution right, because it definitely satisfies that equation. All right, let's look at another example. This one, we've got d squared plus 4d plus 13 operating on y, and it's equal to 0. So this auxiliary equation is just the same one in r's, right? So r squared plus 4r plus 13 equals 0. Two numbers that multiply to 13 but add to 4, not going to happen. So you can do quadratic formula, or 4 is friendly, so I'm going to complete the square. So r squared plus 4r, leave a little blank, subtract the 13 over, leave a little blank. 4 divided by 2 is 2, and 2 squared is 4. Add that to both sides. This is an r plus 2 quantity squared is equal to negative 9, which means your r will be negative 2 plus or minus 3i. All right, so that means your a is negative 2, your b is 3, and your general homogeneous solution, C1, because we're doing some linear combination of these two independent solutions, right? So we've got C1 e to the ax, so negative 2x times cosine of bx, and then plus C2 times e to the negative 2x times sine of 3x. This is, again, the general homogeneous solution. Okay. And again, if you went to go check this and found, you'd have to find the second derivative and the first derivative, and, you know, this is equivalent to y double prime plus 4y prime plus 13y equals 0. That's equivalent. Yeah. So you definitely, if you would have to find the first derivative and second derivative and then plug it in to check it. I'm not going to bother. I know I'm right. Not always, though. Okay, let's do one last example. Third derivative plus 4 times the first derivative is equal to 0. I'm going to change this to d cubed plus 4d operating on y. Yeah. Well, there's a common d and there's a d in common there, so a d times d squared plus 4. So this auxiliary equation would be r times r squared plus 4 equals 0, which means r is equal to 0. Don't forget about that guy, right? R must equal 0, or r squared plus 4 equals 0, but that gives me plus or minus 2i. So for this one, it's a is 0 and b is 2. This guy is a real answer. We did that the other day. So you've got y is equal to c1 e to the 0x. It's a real one, so you don't add in that cosine and sine in there. Right? And then we've got plus c2 e to the 0x times cosine of 2x plus c3 e to the 0x times sine of 2x. And we, of course, can simplify those because e to the 0 is just 1. So our general homogeneous solution to this differential equation is c1 plus c2 cosine of 2x plus c3 sine of 2x. All right, that's section 3. Tomorrow we'll talk about what to do with repeated roots. Okay. You all have a fabulous day.